Hi, I'm Kieran. The purpose of this video is to explain how I implemented the following four functions for data structures and algorithms, assignment 2. The shortest path algorithm was the function I struggled with the most, primarily because I was overthinking it a lot and found it difficult to correctly implement Dijkstra's algorithm. The main functionality of the algorithm is presented here with these nested for loops, in which the purpose of this section is to store the shortest distance for each vertex in the graph from the source vertex in the map dist. I then use the function shortest path result to backtrack from the current shortest distance of the destination vertex in order to obtain the shortest path. Initially, I found that the algorithm would output the shortest path for all cases in the graph received in the assignment. However, when marking it, I realized that it would fail for other test cases not presented in the assignment graph. To debug this, I implemented the larger, more complex graph into my main.cpp in order to test more test cases. Some of the other challenges I faced included using a vector for keeping track of the shortest distance for each vertex. I found that if I implemented a graph with unordered or large vertex IDs, when referencing a value in the distance vector by index, I was unable to access certain vertices. This was also the reason for using a set to keep track of visited vertices, as I also was originally using a vector in which the same test case would fail. I was able to visualize the strongly connected components function almost instantly after gaining a good understanding of what is considered a strongly connected component in a directed graph. The function essentially just compares if each vertex in the graph are reachable from each other and keeps track of visited vertices in order to avoid duplicates in the result. By utilizing the reachable function I made in assignment 1, I was able to ignore having to directly implement some form of a search algorithm within this function. However, I am aware that there may be more effective methods for implementing this algorithm, as I believe the time complexity for my implementation is big O of n squared. In terms of challenges, the only noticeable one was similar case to shortest path, in which I had to ensure to use a set for keeping track of visited vertices instead of a vector. For topological sort, I utilized recursion by implementing a recursive utility function. After reading into the process for topological sort, I found it relatively easy to implement into code. The algorithm searches the graph by calling the utility function for each unvisited vertex in the directed acyclic graph. So as the result produced by the function is a stack, which was also the case for shortest path, I created a function that converts the result stack into a vector of vertices in order to reduce repetitive code. In the utility function, for each unvisited neighbor of the current vertex, recursion is used by recalling the same function. Then the result is pushed to the stack. I found this function straightforward and easy to implement and didn't face any significant challenges. The low-cost delivery function also utilizes recursion through a utility function. The way it works is by converting the graph passed through the function into a spanning tree using the outTree function from assignment 1. Then the total vertex weight is calculated by summing the weight of each vertex in the tree, except for the source. From this, the utility function is called, which sums the edge weight of each edge in the tree through a recursive search algorithm. By using a tree, the function is capable of generating the lowest cost per person for the cases I tested. However, as I did not test this function extensively, I am aware that there may be some cases which the function does not produce the lowest possible cost per person.